So we just started recording. I would like to welcome everyone to this event that we are organizing to celebrate a little more than 40 years since the publication of the book by Stu, Shapiro and Saul Teukolsky, who are here, and I thank them for agreeing to participate. I'm going to show you a very small number of slides because I want to get out of the way as soon as possible and let them talk, that I put together to introduce the event. Here we go. Okay. And let me share them full screen. Can you see them now? All good?
Yes.
Yes.
Yep. So all I wanted to say is that this is the last, presumably, never say never, in a series of events to celebrate some classic books that have been very influential, certainly for me, but also for most people doing gravity in general and relativistic astrophysics, which is now a very hot topic and maybe was not so much 50 years ago or 40 years ago when these books were written. The first event we had back in May of 2023 to celebrate 50 years of Misner, Thorne, and Wheeler. We had both Kip and Charlie Misner in attendance. Unfortunately, Charlie is no longer with us, but it was a very popular event to the point that we overfilled the Zoom room. After that, we had a second event in October with George Ellis to celebrate 50 years since the publication of the large-scale structural space-time by ISGRG, who wrote the foreword for the 50th anniversary edition, was also there. And we heard some very nice talks about the book. And then we had a third event with Bob Wald and David Garfinkel about the general relativity book that Bob published in the 80s. At about the same time that Bob was working on his book, Stu and Saul were working on the book that we're going to discuss today, which is not so much a pure general relativity and gravity book, but a book on relativistic astrophysics. I would like to say that Kip strongly encouraged me and David to also have a celebration for the 50 years of the book by Weinberg, but because Steven Weinberg, of course, is no longer with us, we ended up not doing it, but we are all very well aware that that book was very influential, especially for the particle physics community. You know, it's not that we forgot about it, but we just decided not to go ahead. Now, the book that we're going to discuss today is Black Holes, White Dwarfs, and Neutron Stars. It came out in different editions. There's the black version and the white version, as you see here. The version that I prefer is the hardcover black one that I ended up buying used many years after it came out because it holds together better than the newer one. And it's a book that I tend to use a lot. In fact, I had to say that Mark Kamionkowski, who's next door, went through the whole book and worked out solutions for a very large fraction of the problems in the book a while ago. And it's a book that we talk about a lot. Let me just introduce the speakers, because as I said, I want to get out of the way. The first of them is Stu Shapiro. Stu is, well, very well known to pretty much everyone here, I'm sure. He has been working for a very long time on numerical relativity and its applications in astrophysics, in particular compact objects such as neutron stars and black holes. Of course, this is a very hot topic now after the LIGO detections, but I would say it was very pressing for them to work on this stuff back in the 70s and 80s. Stu got his bachelor from Harvard in 1969, and then a master and a PhD from Princeton, where his advisor was a certain Jim Peebles. Then he did a short postdoc at Cornell before becoming a professor, first assistant, and then associate, and then full at Cornell. And in 1995-96, he moved to the University of Illinois at Urbana-Champaign, where he has been ever since. Besides the book that we're going to discuss today, Saul was asking him if he has any more plans, because he has been very productive with Thomas Baumgarten. He put together 2 books on numerical relativity, a version for adults in 2010 and a version for beginners in 2021. And this is another book that with Mark Kamionkowski we decided to go through solving the problems, the beginner version, because we are not good enough to do the pro version, but we walk through the problems of the 2021 introductory book to numerical relativity. Stu has published over 400 papers. That's a very impressive number. He has been on the editorial boards of many journals, including Astrophysical Journal Letters, in International Journal of Modern Physics C, Physics and Computers, Classical and Quantum Gravity. And he has advised a large number of students and postdocs. Among his honors, he was elected a Sloan Fellow in 1979. He got an award for the book that we're discussing today in 1984 from the Association of American Publishers. He was a Guggenheim Fellow, and he won first prize for the IBM supercomputing competition in 1991. He's also a fellow of the American Physical Society, of the Institute of Physics in the UK. And very recently, I was in the audience of his talk in 2018, when he received the Bethe Prize from the American Physical Society. Saul is at least as well known as Stu. He has been doing fundamental work on black holes. He's one of the few people in this call probably who has an equation named after him. He worked a lot on general relativity, perturbations of black holes, relativistic astrophysics, computational astrophysics. Like Stu, is one of the pioneers on numerical relativity, and these days is very involved in a large collaboration at Caltech Cornell called the SXS collaboration that is being used to produce templates for LIGO now and for this in the future. He got his bachelor in 1970 in South Africa at the University of the Witwatersrand. And then he moved to California, where he got his PhD with Kip Thorne. Notice that both advisors got Nobel Prizes, so we're waiting for you guys to get yours. And in 1973-74, he was a Tolman Fellow at Caltech. Between 74 and 99, he climbed the ladder from assistant to associate to full professor at Cornell. In 1999, he became the Bethe Professor at Cornell, position that still holds to this day. And since 2017, he decided to move back to sunny California, at least to spend some time of the year there, where he's the Robinson Professor of Theoretical Astrophysics. Saul published over 250 papers and several books. Probably the most famous, besides the one that we're celebrating today, is the series of numerical recipes books, first in Fortran, then in C, then in C++. I own, I think, pretty much all of the versions. And he got a number of honors, including the Sloan Fellowship, the Guggenheim Fellowship, the Forefronts of Large-Scale Computing Award. Is a fellow of the APS, of the American Academy of Arts and Sciences, of the National Academy of Sciences. And after the detection of gravitational waves, he was also acknowledged with the Dirac Medal by the ICTP in Trieste, and with the Einstein Prize from the American Physical Society, together with my friend and postdoc advisor, Cliff Will. So that's my intro, and I'll get out of the way as I promised, and I will let Stu and Saul talk about the book.
So I'm sharing my screen. Can you all see it?
Yes.
Good. Great. Well, first, let me thank our hosts, Emmanuel Berti and David Garfinkel, for organizing this event. Certainly quite an honor for us to be participating in this. And I guess it's an indication that longevity does have its virtues. As you see in front of you, as Emmanuel showed, our protagonist, our book, where the first printing is on the lower left, the one we two like best, and then the subsequent and current printing on the right. And I should point out that we're rather proud of the cover that's shown here, since we designed the illustration ourselves. Let me start by telling you some of the early seeds that were sown that gave rise to this book eventually, by taking you back to 1975, when a lot of you probably weren't even born. At that year, I was a postdoc at Cornell, and I was asked by the department if I would be willing to teach a course that semester in the spring. And the reason was that a couple of the faculty were going on leave, and there would be a gap in the course curriculum that semester, and they needed someone to fill it in the general area of high energy astrophysics. And I was promised that Franco Pacini would be visiting later in the semester and would co-teach that with me. And I was also told that I could choose any topic that I wanted to under this umbrella to focus on. So I thought it might be fun, and I accepted that invitation and designed a course called The Physics of Compact Objects, in part because that was an area in which I was doing research, and in part because that was an area in which I didn't know enough about and really thought it'd be fun to learn. So I began to prepare lectures, and as well a notebook of lecture notes for that semester. I actually found that original notebook on my shelf a few weeks ago in preparation for this event, and opening it up, I look at the lectures and the course outline, and I see that many of the topics that I talked about that semester found their way into our book eventually. In fact, I talked about all three of these compact objects, white dwarfs, neutron stars, black holes, first in their so-called ground state, where they were spherical, non-rotating, whole degenerate objects in isolation from everything else. And then I subjected them to perturbations like magnetic fields, rotation, thermal effects, accretion, etc. A lot of the effort was spent on accretion onto compact objects for a couple of reasons. Number one, that was an area in which I was doing research at the time. And also that was an area that was of great excitement because for the first time, binary X-ray sources had been discovered. The Uhuru observations, Uhuru satellite observations had told us that there were compact objects in binary orbit around normal stars accreting gas. And that was the motivation for talking about accretion. Now, there was no good textbook that I could adopt at that time, otherwise I would have. Instead, I had to compile my notes from various references and review articles and journal articles. That is how the course developed. Now, unfortunately, Franco Pacini, who, by the way, was the individual you may know who first proposed the oblique rotating magnetic dipole model as the engine that powered pulsars, Franco never showed up that semester. His visit to Cornell was delayed until the summer, till after the semester, so my lectures continued all the way to the end, as did my notebook, which in fact I had typed up. Well, in fact, I taught this course for the next couple of years when I became an assistant professor at Cornell. But then in 1980, I got the bright idea, wouldn't it be great to expand and rigorize and tighten up these lectures into the form of a textbook, since none existed. And who better to ask to join me on this endeavor than my colleague Saul Teukolsky, with whom we had collaborated already on a number of projects. So I think I handed the notebook to Saul, and told him, take it home, look at it, and see if there's anything to it. And he came back, and yes, writing a textbook would be a good thing, and yes, he would join me on that effort. And that's how this effort began. So I'll come back and tell you some anecdotes later, but let me turn the mic and screen over to Saul and get his take on this story. I'll stop sharing.
Okay. Can everyone see that?
Yes.
Okay. Okay, so the reason I said yes to Stu was that I thought this would be easy. I mean, after all, you know, he had a set of notes. You know, I would put in a few little, you know, edits here and there, and, you know, let's start finding a publisher, right, kind of thing. Well, any of you who are ever tempted to write a book, don't, okay? You always think it's going to be easier than it actually turns out to be. And somehow your hubris gets the better of you, you know. The reason that physicists write books is because they think that nobody else's book is any good, and the way that they see things is the right way, and surely everybody else will agree. Okay, and you're wrong. Just, I finally learned that. I'm not going to write any more books. So let me show you some of the strange things that we had to do. Now, remember, this is, you know, around 1979, 1980, when we started this project. And, you know, Tech and Latex only came out in the mid-1980s. So this is, you know, still in the Stone Age as far as scientific publication. So let me just show you a few things. I went through some old folders that I had kept. So you all know about the expression cutting and pasting. Well, how do you cut and paste when you don't have a mouse or a touchpad to select things with? So the answer is you, all right, so this is a yellow pad, you know, a sheet like this, you know, one sheet. So that's the yellow background, and you can see that's my handwriting on the top. So I started writing something. Then you'll see some typewritten text. That was from Stu's notes. And then his handwriting, he'd made some edits to it. And then I've written something, and then down below there's a Xerox of some notes, handwritten notes of his. And if you look carefully, wherever there's a change in the handwriting or the color, you'll see on the left there's some darker thing. That's some Scotch tape, and that's the pasting. Now that shows what amateurs we were, because the real experts at this, like Kip Thorne, for example, I saw some of his cutting and pasting. The real experts used a special glue called rubber cement. And this had the virtue that if you changed your mind and wanted to peel off what you had pasted and put it somewhere else, it didn't rip the paper the way Scotch tape does. So this was a very difficult process. And God forbid you changed your mind about the order of the equations. So here is something we prepared for the typist, an equation conversion chart, when we went from one draft of the book to the next, and how the typist had to take the old equation numbers and renumber them according to the scheme. And then, of course, since this is very error prone, we had to spend time proofreading all of this. Okay, so again, something you don't have to do anymore with LaTeX. What about the figures? Well, here is a hand-drawn figure that Stu made. You can see, first of all, it's on graph paper. The sketch is pretty good. I left this kind of thing to Stu, who's more artistic than me. And then to turn this into production quality figure, the department employed a full-time person, a draftsperson, who would take this and turn it into something that could be put into the book. So this is the figure that actually went to the printer to appear in the book. And if you look at those curved lines where it says neutron stars and white dwarfs, every time you had a curved line, if it was a plot or something like that, the question is, how do you get a smooth curve? And the answer is, the draftsperson used a spline. Now, a spline in those days was not some mathematically formulated curve like it is today. A spline was actually a flexible metal strip. In fact, in the 19th century, I believe that these things were made out of lead. I think that when, the dangers of handling lead were discovered, I think they used some other, maybe it was wrapped in plastic. But anyway, you would lay this down on the paper and bend it to the shape you wanted, and then you could draw a nice smooth curve. So that's the origin of the word spline. What about index, right? The index was made with index cards, right? So not only did we do the index, but also the references. So here's one, an original. It's from the beginning, I think it was maybe the first one in, it's A. So you had this, and we would prepare the indices, the references that was done this way. At the bottom, you will see 406, 409, 417. Those were the final page numbers in the book, so we could do the author index. Right? This was a proper book. Not only do we have a subject index, we had an author index, as well as references. And these were stored in a box. Okay, you can see this is half the alphabet. You can see on the left side of the screen the second half of our box of references. And then the poor typist had to go through this and turn it into something to give to the printer. Now, what about the title? Well, the title of a book is very important. And you can see this is, again, I don't know which version of the book this was, but if you look at the title on the left there, you'll see it says the physics of, and then something has been crossed out. So it's actually the physics of compact objects, white dwarfs, neutron stars, and black holes. Now, being physicists and rather nerdy, of course, the order we chose for white dwarfs, neutron stars, and black holes was in order of increasing compactness. Right? I mean, isn't that logical? But then, of course, maybe we should have done it the other way, black holes, neutron stars, white dwarfs in descending order. And we'd already decided maybe not, to shorten the title, leave out compact objects. So it was the physics of white dwarfs, neutron stars, and black holes, or the physics of black holes, neutron stars, and white dwarfs. And we couldn't make up our minds, so we asked my wife, who I think is actually on the call today. And she shook her head and she said, you guys, no clue. The most interesting part of the title is black holes. You have to start with black holes. And then it has to be black holes, white dwarfs, and neutron stars, because that just sounds the best. And then if you like, you can have the physics of compact objects. Who cares? So then you can see there in Stu's handwriting, it says black holes, white dwarfs, and Neutron Stars, the Physics of Compact Objects, which of course is a much better title. So it's kind of interesting to figure out how these things happen. All right, so I'm going to stop there and give Stu a chance to talk about some other things. Just stop my share.
Can you see that screen again? Yes.
Yes.
I'll just quickly add that the two secretaries that had to do all that typing, Debbie Stewart and Ginger Whitaker, also had to type all of the manuscripts that faculty were submitting for publications during that time. And we had to steal time in between those manuscripts, some of which were ours, to do the book. That was also a headache. We sent our draft to a number of people, large number of people, to look at it and give us some feedback. And one of the most important persons we sent the manuscript to was our own colleague, Hans Bethe, who, of course, was the foremost authority on nuclear physics and was also world's expert on neutron stars and supernova. And we very much wanted his assessment of what we had done. So we walked over to his office and gave him 3 chapters to look over. And not too many weeks later, he sent me a letter saying that, yes, he'd be glad to read our chapters 8, 9, and 18, dealing with nuclear equations of state, neutron stars, and supernova, and give us comments. Well, that was great. Well, a few weeks after that, got a call from his secretary, Velma, his longtime secretary, called me up. I think Saul was on sabbatical at this point. I got a call saying, why don't I come over to Hans's office where he would give us his impressions of the material. And I said, fine, and started to work my way to his office. When I got very nervous, because a lot was at stake here. This was the world's expert in this area, looking at what we have done, our work over many, many months. What would he think? Well, when I sat down next to him in his office, my fears did not subside when he plopped on his desk a huge stack of notes in which he had his comments. And just glancing over the top, it was clear to me that he had read every line of every page of every chapter that we had given him and had something to say about them, including all the equations. Gulp. Well, as we went through it, my fears subsided because, in point of fact, he was very positive about what we had done. Now, I happen to have his original notes, which I Xeroxed and made some annotations on, highlighted, and you can see that even when he very much liked something, he would tell us, good discussion, he writes here, and nice after a treatment on that particular page, and correct after a derivation we just performed, or very good analysis, he would write. Very good, very useful. So this was great. And he had other small changes, but this was his general impression. We were relieved. Now, later on, when I took the notes home and looked at them, I found something interesting. Here's an example where he wants us to quote a recent paper of his, the famous Babel paper, Bethe, Boehm, Applegate, and Latimer on supernova. And I found it a little surprising and a little amusing. that someone at the age of 75, all his publications and his honors and Nobel Prize would still be interested in having his recent work cited where appropriate. Well, I must tell you that 40 years later, for some strange reason, I no longer find that either surprising or amusing. Nice formula, he writes. Good, agree, fine. Well, Saul and I had very deep respect for our senior mentors. And let me cite John Wheeler as one example. John taught the second semester of my general relativity course at Princeton. And anyone who's ever been to a lecture by John Wheeler knows that he likes to paint the blackboard with elegant figures in multicolored chalk. And whenever he wanted you to focus on a particular part of these figures, he would draw a magnifying glass so that he could zoom in on that region. Well, here on page 378, we borrow John Wheeler's magnifying glass to zoom in on a region near a neutron star. And just so the reader knows we're using this magnifying glass on loan, we have shown his initials on the handle of the magnifying glass, JAW, John Archibald Wheeler. I think I'll let Saul add to some of our anecdotes.
Okay, let me get my screen back. All right, so I'll tell you a few more stories about feedback we got from colleagues. Not everything that our colleagues wrote to us was all, you guys are great and whatever. You need a thick skin to get feedback. So this is some notes that we got from Roger Blanford, who we've given a couple of chapters to. And if you look near the bottom of the screen, page 632, elementary consequences of the black body formula are not major triumphs of accretion disk theory. I can't even remember what major triumph we had touted in the book, but obviously Roger was not impressed. Another example I want to show you about a thick skin comes from feedback we got from Tommy Gold. So for those of you who may not be familiar with Tommy, Tommy was extremely eminent. He was actually the founder of the astronomy department at Cornell. And he was the one who had proposed that the correct explanation of pulsars, namely that they're rotating neutron stars, and also proposed a way to confirm this by looking for the slowing down of the spin period from the power that was emitted and identifying that with the power that was needed to inflate the Crab Nebula. And when this was confirmed a year later, that I think was the turning point when even astronomers conceded that these bizarre objects, neutron stars, had to exist and were the explanation of pulsars. Tommy was just one of these people with poured out ideas, some of which were even correct. For example, in the 1950s, he proposed the theory of human hearing. He pointed out that the Brownian motion of air molecules was big enough that if somebody was talking to you, the pressure wave, the fluctuations that would be produced by that pressure wave in your ear would be swamped by the Brownian motion. So the only way we could hear was if there was some kind of an active feedback mechanism, essentially tuning pieces of the ear to pick out the frequencies of the sound. And he even proposed a way to test this idea, namely, if you could put a very sensitive microphone in people's ears, you should actually hear sounds generated by this active feedback process. And of course, all the neurobiologists and everything scoffed at this, what a ridiculous theory, and blah, blah, blah. Well, it turns out about 20 years ago, Tommy's theory was proved correct. Unfortunately, he'd already passed away. But, you know, endless stories about him. But anyway, Tommy had a very big opinion, big ego. And he would like to tell you about all his great ideas and how many of them were correct and so on. So we had a little trepidation we gave him a chapter to look at. And here's his feedback. And I want you to look at the bottom line here. The preface, now he even read the preface of the book. The preface is too self-lauding, right? We were too full of ourselves in the preface. And, you know, coming from Tommy, this was really too much. Now, I don't know. I don't remember whether we even changed anything in the preface, but it, you know, when I read this a few weeks ago, again, I went back and reread the preface. It seems perfectly okay to me now. So whatever it was that upset Tommy, I think we fixed it. Now, Tommy, you know, I've made him sound like an unpleasant character. He was actually very warm and generous, and actually, you know, a nice person to interact with. And he went through a period, he had a hobby as a carpenter, and he made two beautiful oak tables, one for Stu and one for me. And we still have our table. This is what it looks like. You can see it's just a beautiful piece of work. And he was very proud of the design. If you look at the pedestal, it doesn't have four legs at the corners. Instead, it rests on these two pedestals, one at each end. And the reason for that design was this would not wobble if your floor was a little uneven. And so, so we still have this. Now, here's some feedback we got from Kip Thorne. Now, you'll notice the date at the top there is November 1979, whereas some of the other stuff was 1980, 1981. So Kip, of course, was extremely, I don't know what the right word is, just a very good colleague. He was one of the first people to get back to us. You know, many of the others, things would drag on for months before we heard from them, or even a year or more. And some we never got in, you know, they promised to give us feedback and we never got anything. So we got, you know, quite a few pages back. And something of historical interest is if you look at number 24, page 716, I don't want you to read the whole thing, but I'll read you the end part. The conclusion of greatest interest, this was a proposal for a problem we could put in the book. The conclusion of greatest interest would be that for two black holes of 100 solar masses, the gravitational wave strength would be 10 to the minus 21 at the Hubble distance. One can then invite the reader to speculate as to how frequently such black hole collisions occur within the entire universe. So you can see, even in 1979, this is long before the development of the LIGO as an actual experiment. Remember, the construction was only in the 1990s and so on. And the final discovery was in 2015. Kip was already thinking about merging of black holes at cosmological distances as a source, a potentially detectable source of gravitational waves. And as we all know, this is in fact the predominant source that the LIGO detector is now seeing. So as Stu mentioned, I went on sabbatical 1981, And so around this time, about 1980 or so, I was thinking about where I would go for my sabbatical. And my colleague Bill Press was at Harvard, and he was trying to persuade me that I should come and spend the sabbatical there. And he was one of the people that we had sent a request, would you review the book? And here's what he wrote back to, he sent this to Stu. Send whole book. Also send Saul. We'll keep both for 1 year. So I did end up spending the sabbatical there. By the way, we never got any feedback from Bill. While I was there on sabbatical, you'll see this. This is a letter from Chandra, which I think historians of science might be interested in. It's addressed to me at Harvard, and I'm not going to read the whole letter. He first apologizes for the delay, but then he says, so I'm reading the middle of the first paragraph, but I've now read your various sections with some care, and you are certainly fair, and there are no factual statements which are incorrect. Nevertheless, you can appreciate that there are some overtones which I probably mishear and which others, perhaps more objective, cannot. For those of you who knew Chandra, this is just typical of his style. Therefore, the following comments are to be considered confidential to the extent that they are my personal reactions, and I certainly do not wish others who understand me less than you do to misunderstand. So I'll talk in a minute about what this is about. We'd asked him to comment on the historical pieces that we had about the development of white dwarfs and neutron stars and so on. And as you know, Chandra was the one who really developed the idea that white dwarfs had a maximum mass, and then the same physics would apply to neutron stars. And this led then to the important idea that if you had more mass in a star, you could end up with a black hole. So before I get to what he actually says, the last paragraph is interesting. On a more cheerful note, the last pages of my book, The Mathematical Theory of Black Holes, went off to the publishers 2 days ago, and tomorrow we leave for India, principally to see the high peaks of the Himalayas. So this is 1982. The book came out, I think, in 1983. And as you know, it's what's the word? It's not an easy book. And Chandra really struggled to really get through that stuff. So some of the interesting tidbits was we had repeated the story of the astronomers Bader and Zwicky, who had been the first to propose the idea that neutron stars might exist, and Chandra was very down on them. He recounts in the letter that because they didn't seem to be aware of, they didn't propose a mechanism. They just said they were trying to explain the energy of supernova explosions. And I think they correctly had the idea that the binding energy of a neutron star would be numerically the kind of energy you would need. And that's turned out to be correct. But because they didn't fill in the steps in between, how did you go from a regular star to a neutron star? Chandra was not buying this. And then similarly for the famous papers by Oppenheimer and his students, these were written, if you remember, right before he went off to head the Manhattan Project that built the atomic bomb. These were the papers where they calculated in detail properties of neutron stars and of gravitational collapse to a black hole. He was, and I think correctly, he was irritated that they did not cite, they did not even talk about the maximum mass, nor did they cite his work. And I think that was something that, that was an oversight on their part. And then, of course, there's the famous controversy about Eddington. Just remind you that Eddington was in the 1930s when Chandra was a graduate student at Cambridge. Eddington was sort of the most famous astronomer in the world. And right after Chandra had presented his work on the maximum mass to the meeting of the Royal Society, Eddington got up and out of the blue basically said, this work is all nonsense and has to be wrong. And Chandra did a very good job in public of not showing any open, hurt at what Eddington had done, and maintained that, Eddington was still a friend of his and so on. But in this letter that he wrote to us, it's pretty clear that he was deeply hurt. This letter was written 50 years after the blow up with Eddington. And a lot of the other historians had ascribed the fact that astronomers neglected or ignored Chandra's work to Eddington's influence. And Chandra is not buying that. He says that astronomers, really did this on their own. No serious astronomer really accepted my results. And then he actually lists in the letter 4 awards, like the gold medal of the Royal Society that he got for his work in astronomy, and none of them cited his white dwarf work. And he, speculates whether it was because it was controversial. And what's interesting is that 1 year after writing this letter to us, he won the Nobel Prize in physics. And the citation is sort of hedging for his theoretical studies of the physical processes of importance to the structure and evolution of the stars. So it's kind of acknowledging that he had an impact, but still not using the word maximum mass or white dwarfs. And it's really, really peculiar how human beings can behave. All right, so that's the end of what Stu and I have prepared. And so I'm going to stop sharing, and then we'll happy to open the floor for discussion.
Thank you so much for all of the historical tidbits. I learned a lot, for sure. Who has questions? Sad.
Hi, Stu, and hi, Saul. Congratulations on this occasion. I noted something that Kip wrote, which is really very interesting. He says these technologies would require probably third generation technology or third generation gravitational wave detectors. I couldn't catch it fully, but he was absolutely visionary in that respect, that he's not just thinking about just some gravitational wave detectors, that they will have many generations. And eventually we will get there and we will detect them. Absolutely stunning. I don't know if Kip is online, but that was fantastic. But it is also very interesting that although almost no astronomers believed in binary black holes, this was something that was also thought by Kip as an important source. I think we were just learning that black holes were real. Stellar mass binary black holes were not yet detected anywhere. Even now, there is no other way we see them. So it's really very nice to see these words coming in. But what about you guys? Did you guys really thought that gravitational wave astronomy will one day be a reality, and we need to take that seriously at that time?
Well, I'll begin by saying, we assumed, writing the book, that readers would not necessarily have a background in gravitation, in general relativity or astrophysics. So we had to develop and introduce general relativity, at least so far as they could build equilibrium stars, understand their stability, throw geodesics of massless and massive particles onto Schwarzschild and Kerr black holes to get their understanding of space-time geometry. And fortunately, we developed the quadrupole formalism to deal with gravitational radiation and have a whole section on the inspiral of two objects in circular orbit. At that time, already the Hulse-Taylor pulsar had been discovered. And we have a long unit on that object, anticipating its eventual very accurate confirmation of the quadrupole formalism. So yes, we were well aware that gravitational radiation was on the frontier, but of course there was even LIGO was not a, if I remember correctly, that name didn't exist, let alone LISA. But I think it was just the bar detectors of the day, the Weber bar detector, which I think we still had some confidence in at that time and wrote about in the book.
Yeah, I can just add that the sections in the book on general relativity, they appear spread over 3 chapters. Those are sections that we're very proud of, in the sense that, you know, when you write a book like this, which is a combination of theory and observation, of course, the observational part goes out of date, and it's, you know, you can't use that. There's been so many advances. But we hope that the theory part would stand up. And I think the general relativity, you know, personally, if I have a new student now and they haven't had a GR course, I give them those sections to read. I think they're better than what you find in many of the books. I mean, for example, we thought it important to include an explanation of how you make measurements in general relativity if you can use any old coordinates. And the reason that's there is because when I was an undergraduate and trying to teach myself GR out of the books that existed then, nobody would explain to me how you made a measurement. So finally, when I took a course from Kip, I learned the answer to that and made sure that that's in the book.
And just to expand upon what Saul was saying, I have a team of undergraduate research students who are still working their way through the undergraduate physics curriculum. I usually assign to them 3 chapters in that book to read over the summer. Chapters 5, which introduces GR and uses their knowledge of Euler-Lagrange equations to derive geodesics. Chapter 12 on black holes, uses those geodesics to probe their geometry. And I think it's chapter 16 on gravitational radiation, which we build by analogy with electromagnetic radiation, something they've already studied. So I agree with Saul. We're pretty proud of those chapters. And similarly, for the relativists who take the course but don't have any astrophysics, we had to introduce things like stellar evolution, radiative transport, and stellar dynamics at several points in the book. And we have sections on those very subjects as well.
Yeah, maybe I should also acknowledge that my very first research seminar on neutron stars and black holes, I benefited a lot from reading this book. Thank you very much.
Thank you.
There's a question from Cher, Scarlett.
Hi. So I am an undergraduate student, and I recently did a directed study on the physics of compact objects. And this was one of 4 books that we used, and we actually used it for GR. And just before I ask my question, I just wanted to say I really appreciated the book. And now I'm in modern physics this semester, and it actually, I feel like I have such a huge leg up on all of these students around me just from studying compact objects, because so many of the, equations of state and these, discrete physics, you kind of learn, and I had to learn like really fast. But yeah, it was a really great book, and I feel so blessed to even, be a part of this community and to know Saul And one of the things that I love about studying physics is that physics is really taught from like a historical perspective. Like when I took chemistry and biology when I was younger, and even in college, like I don't really learn so much color in the order of like the way that things happened historically, but you really do with physics. And that's one of the things I love about it. It feels like even though like it's a very rigorous scientific field, there's all these like humanities like just kind of baked in, and you get to learn a lot about people. And I really loved like hearing some more backstory about this book writing process, and kind of, I guess, you know, where Stu and Saul were when I was being born. And here I am now. So my question is, so back then, like where you were when you were writing this book and where we are now, like I feel like I'm kind of like, you know, in the beginning state. If there was a group or a couple of young physicists as you were now, what do you think the frontier would be? I know you said don't write a book, but if they wanted to, if they were, where do you think we are, like in terms of like similarity, where, you know, now we're discovering gravitational waves, whereas you were theorizing them? Where do you think we are now that's similar?
Yeah. Stu and I are each waiting for the other to speak up.
I'll start. Clearly,
Yeah.
gravitational radiation, gravitational waves. The next stage is LIGO and LISA, and the new detectors that are in the works or in the design stage. That's clearly the frontier of a lot of this. The James Webb telescope finding black holes ever further and further out. And I think although we see supermassive black holes in almost every active galaxy and quasar, we really don't know how they arise. There's some good theories about it, but that is a frontier topic, I think, as well as the usual cosmology questions of dark energy, dark matter. Those are some of the very big questions. And is general relativity right? It's passed all the tests. It continues remarkably well, whatever we throw at it, but we continue to test it in new regimes, and that's what gravitational wave observations are fine-tuning.
I don't have anything to add.
Okay, then David has a question.
Yeah, so among your anecdotes, you mentioned interacting with and getting reactions from Tommy Gold. And one sort of very interesting comment that you made was that Gold had a lot of ideas, some of which were right. So as you know, one of Gold's ideas, actually the idea of Bondi, Gold, and Hoyle, is the steady state universe, which turned out to be spectacularly wrong. And I mean, not only Gold, but also perhaps even more so Bondi and Hoyle were brilliant physicists with great achievements. Do you have any insight from interactions with Gold about, how it is that otherwise brilliant people can get, sort of attached and locked into wrong ideas?
Yeah. I mean, you have to remember that when those ideas were proposed, like in the late 1940s, there was basically no data, right? I mean, cosmology was, a backwater in the minds of physicists. And I think that, people working in cosmology today, it's very difficult for them, because we're now in the era of almost too much data. It's precision cosmology, that it was a blank canvas. And so it was a perfectly reasonable theory to propose this at that time. What's interesting psychologically, I mean, the thing that really killed the steady state model was the discovery of the microwave background, because that proved that in the early, the universe was not the same always, that early on it was much hotter than it is today. And Tommy never accepted that. He spent all of the rest of his life trying to come up with ways to explain the microwave background, not as leftover heat from the Big Bang. All kinds of things with various, crystals in space that were reflecting light. And I mean, he wouldn't give up on that idea. And kind of sad. If people are interested, I can tell the story of how Tommy became an expert carpenter. I don't know if people are interested. I mean, I could never make a table like that. I don't know if anybody else here can. Tommy grew up in Vienna, and when he was 19 years old, the Nazis invaded Vienna. He was finishing his first year of engineering in college. And his family fled, ended up in London. And what happened was the British interned everybody from German-speaking countries. They wanted to sort through and make sure there were no spies among them. And Tommy got sent to an internment camp in Canada. And after a few weeks there, they lined everybody up and started going down, asking each of them, what was your profession? And Tommy realized that if he told them that, he just finished his freshman year, doing calculus or whatever he'd been doing, he'd end up being assigned to scrub the toilets. So when it came to him, he said, I'm a foreman carpenter. He knew nothing about being a carpenter, but he'd figured out he could read a blueprint and tell them, how long to cut the boards and all of this. And sure enough, that's what happened. He got put in charge of the rail carpenters, and they built the barracks and did all these things. And he was there for almost a year, and the rail carpenters basically taught him carpentry. And he told us the story that this is how he got to be essentially professional level at doing this.
You commented, you asked about the steady state theory and gold and oil sticking to it. They're not the only ones who made big mistakes. You may know that we recount in the book that Landau, who developed the notion of a maximum mass for neutron stars, understood that a simple implication of the theory was that stars bigger than that might undergo collapse to what he thought was a point mass. And he basically said, in the end, this is absurd. The laws of physics must come into play to prevent this from happening. And he was not alone in that notion. You know that Eddington didn't buy into the notion either. So, we forgive these great men of their mistakes, but they did make them on occasion.
You have a question? Would you like to ask a question? You're muted.
No, it was a comment that I went to a seminar by Dennis Sharma, who was another keen supporter of steady state in one phase, in which he recanted on the grounds essentially of the microwave data. But his opening comment reinforced what was just said, that when he started work in cosmology in 1950, there was only one known fact about the universe, and that later turned out to be wrong. It being, of course, the value of the Hubble constant.
Are there other questions? If not, I would like to ask one. So I think So you started by giving the very useful advice to all of us that if we want to write a book, we should not, and explaining why. But then I think you gave us very good advice about what one should do if one persists and actually wants to write a book, by saying that, you know, observations come and go, but good theory stays. And I think that's one of the things I really like the most about your book, that incredibly 40 plus years after it was written, every single bit of physics in that book is still perfectly valid because you made a fantastic choice of topics. And so I would like to ask you the same question that we asked to other people in this series of books, which is, if you could go back in time, which we know is probably forbidden by the laws of general relativity, and make different decisions about the topics that you included and the ones that may want to add in retrospect, what would you do?
I can begin by saying I did make, anticipating someone might ask, what would we put in the book today that we didn't put in it? And this has to do with things that didn't happen or we didn't know much about at the time. The list that I have includes more about gamma ray bursts. Now that we've seen merging neutron star emit both gamma rays and gravity waves, we think we know what they are all about. LIGO Virgo, the whole story there, we would have to put in, and this compact binary merger would emphasize to a much greater extent. The Event Horizon Telescope, we clearly would have a picture in the book showing their wonderful shadowing that the M87 and Sagittarius produces. Binary pulsars, we had one, we had the whole tail, but now there's a whole list of binary pulsars with very reliable masses, including the fact that neutron stars must be bigger than 2 solar masses. That's a fact that's not in the book. We would probably put that in bold. The nicer observations, which tell us something more about neutron star radii. Now, we already knew a bit about radii, and there were things discussed in the book having to do with observations, the Einstein Observatory X-ray telescope, and gamma and X-ray bursts. But now the nicer observations, I think, are a little more reliable. Rotating neutron stars. It's curious, we have a whole discussion of rotating neutron stars in the book. And like other things we tried to do, we built that discussion on a simple analytic, albeit approximate model that students could follow and ascertain the essence of what's going on. But at the time we wrote it, there were no real numerical calculations that showed the structure of a rotating neutron star. That happened a little later. And Saul and I, with a postdoc at the time, Greg Cook, in fact, went into that area ourselves. But we would now include those more serious calculations of rotating neutron stars as well, which talked about things like supramassive and hypermassive neutron stars, which weren't even discussed at that time. And then the I love Q relations might have also be of interest, these relations that have a universal connection between moment of inertia, quadrupole moments, and love numbers. Those are just a few topics I jotted down just yesterday on what I might throw in to a book at this time.
So you do have ideas for another one to answer?
Absolutely not.
Okay.
The one thing I wanted to do, there's some, believe it or not, there's some typos in our book. And I've accumulated a list of a few of them. Saul probably has a few. And I once asked our publisher if we might have a version which corrects those typos. And the answer was no, that would be too difficult, too expensive for them to do, unless, of course, we wanted a whole new edition. That I was discouraged from doing, in part because of something Saul told me, I think it was Saul, about Chandra. And, Chandra wrote many books in his life. Stellar structure, radiative transport, ellipsoidal figures of equilibrium, general relativity, as we know. But when Chandra finished research and then wrote up a book, he would leave that topic, never to return again, and never to do another edition of the book. I like that idea.
So would you like to add?
Now, the only thing I'll add is if someone were to write a book today that included all of the topics we had, plus what Stu mentioned, it would be this thick. The subject has really, it's just hard to keep track of everything. So I think it would be a real challenge to try to get a decent size textbook today that really covers the field of relativistic astrophysics.
I think that means that you made a good choice of topic and you wrote it at the right time, which sometimes is critical, right? Okay, I don't see hands up. So I'll wait a few seconds just to see if someone wants to ask one last question before we wrap it up. And if I don't see any hands up, I would like to thank you both. I think it was very informative and I found it fascinating. So thanks again. And we're going to upload this. Thank you.
Thank you.
Thank you. That was very interesting.